This is Babitha, working as Assistant Professor in the Department of ECE, Institute of Aeronautical Engineering. Today I am going to discuss about the bipolar junction transistor and its configurations. So while coming to the contents, here I am going to discuss about what is meant by transistor and what is the construction and operation of the transistor. And also I am going to discuss about the different configurations of the transistor. So here while coming to the definition of the transistor, bipolar junction transistor, here it is a solid state electronic device that is used to control the flow of current or electricity in the equipment or in the electronic equipment, and it is usually consists of small block of semiconductor with at least 3 electrodes. So that is nothing but we can say the transistor is a 3-terminal device which is used to transfer the or in order to control the flow of electricity in the device. So it consists of 3 terminals. Those are base, emitter and collector terminals. These are the 3 different terminals of the transistor. And here we can observe the different types of the transistors. Previously in the olden days, transistor was implemented with the vacuum tubes. These are the vacuum tubes. And so transistors are implemented with the vacuum tubes first, and later on it is invented with the semiconductor materials by using the P type of semiconductor material as well as N type of semiconductor material. Next invented the transistor. So this is the first transistor invented in Bell Laboratories in the 1947, and later on it is implemented in this way with the 3 terminals. This is the emitter, base and collector terminals. So generally this kind of transistor we are going to utilize in the laboratory purpose in order to do the experiments for amplification as well as switching, and later on it is implemented in this way in the form of chip. It is also having 3 terminals. Those are emitter, base and collector. So these are the different generations of the transistor. First one is this one, next this, and later on now we are utilizing this kind of transistors. And before going to the construction and operation of the transistor, first of all we have to know what is meant by transistor and why we are coming from the transistor here, even though we are having the diode. First electronic component or electronic device we are having the diode, and later on why we are moving for the transistor we will see now. So here I am considering the normal water pipe. This one I am considering here it as PN junction diode, PN diode. So it is having 3 terminals, that is anode and cathode terminals. So here PN junction diode is a unidirectional device, so it will flow the current from anode to cathode. That is nothing but here this particular pipe will allow the water and it will pour from the cathode here. In this case, there is no control of the current here. There is no control of the current in the case of PN junction diode. If you want to control the current here, we have to change the biasing. We have to increase or decrease the biasing, or we need to remove the biasing in order to control or stop the flow of the charge in the case of PN junction diode. So here this flow we are taking here it as the current conduction in the PN junction diode. So if we want to change the conduction state or current flow, we have to remove or adjust the biasing conditions of the diode. So the diode itself, it cannot change the variation of the current. But this particular tab here I am taking here it as bipolar junction transistor. So this bipolar junction transistor is a 3-terminal device, that is emitter terminal. That emitter terminal we will represent here it as capital E, and this terminal is the base terminal. The terminal we are representing here with the capital B, and this terminal, I am calling it as the collector. I am representing it with the capital C. So here BJT consists of 3 terminals. So here the function of the tap is to control the flow of the water. So in our case, it will control the flow of the charge. So here the emitter, the function of the emitter is to emit the charge carriers, that may be electrons or holes. Okay, the function of the emitter is to emit the electrons, and the function of the collector is to collect the electrons. Whatever the charge carriers which are generated by the emitter are collected by the collector here. But what is the function of the base here? So the function of the base is to, in order to control the flow of charge carriers and in order to control the flow of current in the device. That is nothing but if we turn on or turn off this base terminal, we can able to off or on our charge carrier flow here. That is nothing but water flow, we can say, and we can able to reduce or increase the pressure of the water. That is nothing but we can able to increase or decrease the pressure of the charge carriers here. So here we are not at all changing the biasing conditions of the transistor. We are not changing the biasing conditions. By using the base terminal, we are controlling the flow of the charge carriers. So that is the basic difference between the PN junction diode as well as the transistor. Both are used for current conduction purpose. And PN junction diode we can use for switching applications. We can use it as open switch in the reverse biasing condition and closed switch in the case of forward biased condition. So in the case of BJT, it will be utilized for both the switching operation as well as amplification operation. So these two are the basic applications of the transistor here. So it can act like an open switch as well as closed switch, and it can also amplify the signal. So the function of the amplifier is to amplify the weak signal. So next we will see the construction of the bipolar junction transistor here. So to construct the bipolar junction transistor, here we have two choices. That is, if we take N type of material and P type of material here we can take either two pieces of N type of semiconductor material and one piece of P type of semiconductor material. So by using this particular combination, we can make one type of transistor, or else we can take two P type of materials and one is N type of material. By using this particular combination also, we can able to form one more type of transistor. Suppose if I am taking two pieces of the P type of semiconductor material and one piece of the N type of material, it is nothing but in this way we'll get here. That is, in between two pieces of P type of semiconductor material, we are sandwiching or inserting one piece of N type of semiconductor material. So it is formed like a PNP transistor here. And similarly, if you take the next combination, that is two pieces of the N type of material and one piece of the P type of semiconductor material. In this case, if we sandwich one piece of P type of semiconductor between the two pieces of N type of semiconductor materials, then we can form the NPN transistor. So from this we can say we are having two types of transistors, that is PNP transistor and NPN transistor. See here, P is nothing but positive P type of semiconductor material. So the majority carriers are the holes. So that's why we are representing with the holes. We are having few electrons also. And similarly, N is nothing but an N type of semiconductor material. So the majority carriers are the electrons and we are having few holes also. And in the P type, again holes, few electrons. And similarly here also, electrons are the majority carriers and few holes. And few electrons here, few holes here. So how we can construct this particular NPN and PNP transistor? Whether we are taking two pieces of N type of materials in the NPN transistor and two pieces of P type of material in the PNP transistor, whether the widths of both the P type and N type materials are same or different, we have to see once. So in that, and considering width of regions of the transistor here. This is the emitter region, this is the base region, and this is the collector region. See, the collector width should be very high. Why? Because the function of the collector is to collect the charge carriers. If the space is very high, means it can able to collect more number of charge carriers and it can store more number of charge carriers. And next, the width of the emitter. Okay, first highest width for collector, and next emitter, and next the base width. Base should be very thin here. Base should be very thin. Here our intention is to emitter should emit the charge carriers and collector should collect the charge carriers. So if base terminal is width is very high, means so much recombination will be there so that we can get less current across the collector. So that's why, because of that reason, we are making width of the base region is very less. So from this we can say collector is having highest width, emitter is having moderate width, and base is having less width. Okay, this is very important thing in the construction of the PNP as well as NPN transistors. And similarly, doping concentrations of the regions. Suppose if you take the emitter should emit the charge carrier, so that doping should be very high in the case of emitter here. And next collector, and next base. So why we are making high doping for the emitter, means in order to produce more number of charge carriers, and later on why we are making moderate doping in the collector, means in order to get the high current across the output, that is across the collector. And why less doping in the base, means in order to reduce the recombination process and in order to improve the output current. So here from this we can say emitter is heavily doped, collector is moderately doped, and base is very lightly doped regions here. And here, can we interchange the emitter and collector terminals? No, we cannot interchange the emitter and collector terminals. Why? Because the function of the emitter is to emit the electrons and the function of the collector is to collect the electrons or holes, depends upon which type of transistor we are taking. So the functionality wise, both the region functions are different, so we cannot interchange. And if we take in width wise also, widths of both the emitter and collector also different, so we cannot interchange. And if we take in the doping wise also, doping also different in both the regions. So because of these reasons, because of the doping level, because of the width of the region, and because of the charge carriers or functionality, we cannot interchange the emitter and collector terminals here. So in this way only we have to take here. So this is about the construction of the bipolar junction transistor. So in the case of diode, we are having only P and N type of material. So if we sandwich both the P and N type of material, we will get the PN junction diode. We will form the single junction here. But in the case of PNP and NPN transistor, we are having two junctions here. This is one junction at PN regions, and this is one more junction at NP region. So this junction J1 is also called as base to emitter junction, and junction J2 is called as collector to base junction. Okay. So in the case of a transistor, we are having base to emitter junction as well as collector to base junction, and these same things applicable for the NPN transistor also. And we can also form the transistor by using two diodes. Here I am taking the two diodes PN and NP. So if we connect both the cathode terminals of the two diodes, then we can form the PNP transistor. See here, this is the cathode terminal and this is the cathode terminal of the second diode. If we connect these two terminals, it becomes the cathode, that is nothing but N type, and here it is anode P type, and here it is anode P type. So it becomes the PNP transistor with the three regions. And similarly, if we connect the two diodes back to back, or else if we connect the two anodes of the two diodes, then we can make the NPN transistor. So by using the P-type and N-type semiconductors, we can construct the transistor, as well as by using two PN junction diodes also, we can construct the NPN as well as PNP transistors. And while coming to the symbols, so this is the symbol of the PNP transistor, and this is for NPN transistor here. So here this arrow indicates the current direction here, emitter current direction. Always in the PNP transistor, emitter current direction is inside. So to remember this, we can call it as point in permanently. That is nothing but the emitter current is always point in permanently. PNP. That is nothing but emitter current is always inside permanently. And if we see the symbol of the NPN transistor, we are having three terminals. Okay. In this case, the emitter current direction is outward. So here we can say never point inside. Never point inside. That is nothing but the emitter current direction should not outside in the case of NPN transistor. So how we are mentioning the directions of this PNP and NPN transistor currents, we can understand once we see the operation of the transistor, that we will see in the later slides. Okay. And next, if we see the regions of operations of the transistor, here in the transistor I have already mentioned we are having two junctions, emitter based junction as well as collector based junction. So by providing the different biasing conditions to your both the junctions of the transistor, we will get the different regions of operations for the transistor. For that, I am taking first emitter based junction, that is J1 junction. If we apply forward bias to emitter based junction and forward bias to collector based junction. In this case, both the junctions are forward bias so that the transistor will operate in the saturation region. So the region of operation is saturation. So in this case, it acts like closed switch. So in the saturation region of operation, transistor is operated as closed switch. And similarly, if I apply the reverse bias to emitter based junction and reverse bias to collector based junction. So in this case, the transistor will operate in the cutoff region. So in the cutoff region, it acts like a open switch. So when the transistor is operated in the cutoff region as well as in the saturation region, means we can utilize here it as switching application, open switch as well as closed switch. And if I forward bias the emitter based junction and if I reverse bias the collector based junction, so in this region, this particular region of operation, we can call it as active region. So in the active region, the transistor we can utilized for amplifier application. That is nothing but for the amplification purpose, we can utilize the active region of operation of the bipolar junction transistor. And if I apply the reverse bias to emitter based junction and forward bias to collector based junction. So in this region of operation, we can call it as inversion region. So this particular region we cannot use for any practical applications. Only these three regions we will utilize in order to get the switching as well as amplification operation. So these regions of operations are very, very important in the case of bipolar junction transistor. And once we see the operation, we can understand the regions of operation. And next we will see why it is called as bipolar junction transistor. BJT is called as bipolar junction transistor. Why we are calling it as like this means, here transistor is made up of P type of semiconductor as well as N type of semiconductor. So we are utilizing both the type of semiconductor materials to construct the bipolar junction transistor. So in the P type of material, we are having the holes are the majority carriers, and in the case of N type of material, we are having the electrons are the majority carriers. So in the case of bipolar transistor, the current conduction is due to the majority carriers as well as minority carriers. So that's why it is called as bipolar. And why it is called as junction? See, here we are having two junctions, base to emitter junction and collector to base junction in the case of transistor. So it is having two polarity charge carriers as well as two junctions. So that's why bipolar bijunction actually. So it is simplified as bipolar junction. And why it is called as transistor? Here this transistor word came from two words, that is transfer plus resistor. That is nothing but transistor. The function of the transistor is to transfer the signal from low resistance region to high resistance region. So why I am telling like this means, generally if you want to operate the transistor in the amplification mode or in the active region mode, in that case base to emitter junction is forward biased and collector to base junction is reverse biased. So once the base to emitter junction is forward biased means the resistance of this one is very low. Once it is base to emitter junction is nothing but it is like normal PN junction diode only. BE is one junction, one diode, and CB is one more diode. Why? Because if we connect the diodes also, we can make the transistor. So BE is forward biased means it acts like a forward biased PN junction diode. So for the forward biased PN junction diode, the resistance is low. And here collector to base junction is reverse bias means it is also acts like a one of the diode. So once the diode is in reverse bias condition means the resistance is very high. So this base to emitter junction I am taking here it as input junction and collector to base junction I am taking here it as output junction. So this resistance I am indicating with the RA, input resistance, and this resistance I am indicating with RO, that is output resistance. So if you represent this input section as well as output section with the resistance, this is Ri, this is R0. So here we will apply our input signal and here we will observe our output signal in the amplifier operation of the transistor. So that is nothing but here VA is the weak signal we are applying here. Across the output we will get it as the amplified version of the signal here. Here if we write the current equal to VI into RA, input current. And similarly, if we write the output current, that is VI by RA, and output current equal to V0 by R0. Okay, and similarly if we write the input voltage, that is equal to IA into RA. So here the resistance value is very less, the input level is low, and here the output voltage is I0 into R0. So the R0 resistance is very high, so the output level is very high. Here it is low value, here it is high value. So that's why we are telling that the transistor is used to transfer the signal from low resistance region to high resistance region, and from that we can get the amplification. So because of this reason it is called as transistor. So from this transfer plus resistor we are taking transfer from the first word, ester from the second word. So it becomes the transistor. So because of this reason, it is called as bipolar junction transistor. It is having two types of charge carriers and two junctions, and it will transfer the signal from low resistance region to high resistance region. And next we will see the operation of the NPN transistor as well as PNP transistor. For that purpose, I am considering the NPN transistor here. In the NPN transistor, electrons are the majority carriers, holes are the minority carriers. In the P type of material, holes are the majority carriers, and here holes are the minority carriers in the N type of material. So I want to operate this NPN transistor in the active region of operation. How I can get my active region means if emitter base junction is forward biased and collector base junction is reverse bias. When we apply the biasing in this way, we can get or we can operate the transistor in the active region of operation. So that's why I am applying the forward bias to emitter base junction and reverse bias to collector base junction. So forward bias for emitter base junction means emitter is N type of material. So for N, we are connecting the negative terminal of the battery here, and base is P type of material. For P, we are adding the positive terminal of the battery. So once we are providing the same polarity battery to your device, then we can say that particular device is in the forward bias condition. So we can say our emitter base junction is in forward bias condition now. And similarly, for the collector base, we need to apply the reverse bias. So collector is the N type of material. So for that, I am adding or I am connecting the positive terminal of the battery, and base is positive. For that, I am connecting the negative terminal of the battery. So this voltage I am calling it as VEE, and this voltage I am calling it as VCC. Both are the supply voltages in order to make the emitter base junction is forward biased and collector to base junction is reverse biased. So what will happen when we forward bias the emitter base junction? See, the electrons are the majority carriers in the N type of material. Those are repelling from this negative terminal of the battery and they are moving towards the junction. They are moving towards the junction, and it will cross the junction and enter into the base region. Okay. These electrons repel from the negative terminal of the battery and they are trying to diffuse towards the base terminal. So electrons crosses the N region or emitter region and entered into the base region, and some of the few electrons recombine with the holes which are present in the base region or P region of the transistor, and remaining electrons will pass to the collector region. So due to this recombination process, some current will generate in the base. That current we are calling it as the IB. Why I am indicating the IB direction in this way means these electrons are attracting towards the positive terminal of the battery. In this direction they are moving. Always the current direction is opposite to the electron direction. So that's why the base current direction is upward direction. And here, how many electrons are recombining here? Suppose I am sending some 100 electrons from the emitter region. Only some 3 to 5% of electrons only recombine with the holes which are present in the base region, and remaining 95 to 98% of the electrons will move to the collector region. So what will happen in the collector region? See, for the collector we are providing the reverse bias. So the majority carriers of the collector, those are electrons, are moving towards the battery terminal. So because of this movement, the collector current will generate in the collector region that is opposite to the electron flow. And what about emitter current here? See, these electrons are moving in this direction, so the emitter current will flow in this direction. So, the total current which is flowing in the NPN transistor we can calculate by using the Kirchhoff's current law. That is, currents entered is equal to the currents leaving. Sum of the currents entered is equal to the sum of the currents leaving. So here the leaving current is emitter current, that is equal to entered currents are collector current and base current. So the emitter current is the sum of the collector currents as well as base current in the case of NPN transistor. Similarly, if you see the PNP transistor, same I have forward biased the emitter base junction and reverse bias is the collector base junction here. So in this case, majority carriers are the holes. So these holes are repelled by the positive terminal of the battery and they are moving towards the base region, and only few holes are recombined with the electrons which are present in the base region and remaining will enter into the collector region. So in this case, the base current is outward direction. Why? Because these electrons are repelled by this terminal, negative terminal of the battery. So that's why current direction is outward to the junction. And here the minority charge carriers which are present in the P region or collector region are repelled by the negative terminal of the battery and they are moving towards the junction here. So the collector current direction is opposite to the electron flow here. So that's why outward direction. And similarly, the electrons are attracting towards the positive terminal of the battery. They are moving in this way. So the emitter current direction is in this way here. So in this case also, if we apply the KCL, we will get the entered current emitter is equal to the sum of the collector current and the base current. Those are the leaving currents. So if we take the NPN transistor or else PNP transistor, in both the cases, the emitter current is the sum of the collector current as well as the base current. So this is about the operation of the NPN as well as PNP transistor. So next we'll move with the different configurations of the transistor here. So here transistor is having three terminals. Those are base, emitter and collector terminals. So because of having three terminals, we can able to form the three configurations here, that is common base configuration, common emitter configuration as well as common collector configuration. Okay, so why we are making these different configurations means in order to see the characteristics of the transistor here. So to go that, first of all, in the case of PN junction diode, we are having single port or single junction. Okay, so that's why directly we have drawn voltage versus current characteristics, that may be forward or reverse, but voltage versus current characteristics we have drawn in the case of PN junction diode. But in the case of NPN or PNP transistor, anything, we are having two junctions. One is input junction and one is output junction. So one terminal we can take it as common and we can take it as two-port network, that is input port, here it is output port. Okay, both are input port and output port, both the junctions are there. So we have to draw the input characteristics as well as output characteristics in the case of transistor. And these input and output characteristics we are going to see in all the three configurations. So what is mean by input characteristics here? So input characteristics will describe the change in input current with the variation of the input voltage while keeping the output voltage constant. That is nothing but input characteristics are nothing but VI versus IA, input voltage versus input current for different constant values of output voltage. And similarly, while coming to the output characteristics, so these output characteristics will draw with the output voltage versus output current by keeping the input current constant. So these three input and output characteristics we are going to see in all the three configurations. So for that, first of all, I am taking the common base configuration. How we can make the common base configuration? If you take the base terminal as common between the emitter and collector of the transistor, then we can say it as the common base configuration. So here base is common means base is grounding here. I am showing for both the PNP as well as NPN transistor. So here it is the base, here it is emitter and collector terminals. Okay, and we are taking in the active region of operation to draw the characteristics. So emitter base junction is forward biased. So we will get here it as base to emitter voltage, and here we will get it as collector to base voltage. So why I am writing here it as VBE? Why not BEB? Means base is connected to the positive polarity, so that's why VBE. And here also collector is connected to the positive polarity, so that's why VCB. We cannot write VBC. Okay. So to draw the input and output characteristics, we have to know the input-output voltages as well as input-output currents in the case of all the three configurations. So in the case of common base configuration, input voltage is VBE and the input current is IE. So we will draw VBE versus IE in the case of common base configuration to get the input characteristics. While doing this, the output voltage VCB is constant. And similarly, to draw the output characteristics, we have to take the output voltage, that is VCB, and output current, that is IC. That is nothing but VCB versus IC we are going to draw for the output characteristics while keeping input current base current as some constant value. So these are the parameters required to draw the input-output characteristics of the common base configuration. See, in order to draw the input-output characteristics, or in order to analyze the input-output characteristics, we have to take this experimental setup for the common base configuration. So this is common base configuration like a previous circuit, but we included all the voltmeters as well as ammeters and potentiometers in order to see the values, or in order to note down the voltages and currents. So to see the VBE voltage, we are using this voltmeter. To see the emitter current, we are using this milliammeter. And similarly, to measure the collector current, we are using this milliammeter. And to measure the output voltage, we are using this one. So these potentiometers are used to vary the supply voltage. If you vary this potentiometer, there is a corresponding change in the emitter current as well as VBE voltage. And similarly, if you vary this potentiometer, the same variations we can see in the output voltage as well as output current. See how we can get the input characteristics here. See, in the case of common base configuration, this is NPN transistor I am taking, this is emitter, base, collector. So we can also take it as two back-to-back diodes. Okay. So here emitter base junction should be forward biased. This one should be forward biased and this one should be reverse biased. So we are drawing the input characteristics, means we are drawing the characteristics for the input junction. So what is the input junction? The forward biased PN junction diode is the input junction here. So what are the characteristics we are getting in the forward biased PN junction diode? That only we will get in the forward or input characteristics of the common base configuration. In the common base configuration, VB is the input voltage, IE is the input current here, VBE. Okay, for different values of VC. So if you take the germanium type of materials, we will get the cutoff voltage after 0.3 volts only. There is a rise of current here. See, in the case of input characteristics, if we increase the collector to base voltage, that is nothing but different values of collector to base voltages we are providing here. If we increase the collector to base voltage, the emitter current will also increase. Why it is increasing means because of the base width modulation or early effect here. So what is mean by that base width modulation and early effect? We will see now. For that, I am considering the transistor here. This is N, P, N, that is emitter, base, collector. So here VCB is reverse biased. So if it is reverse biased means there is more number of immobile charge carriers in the base region, okay, and less positive immobile ions across collector region. So if we take this total width as base width, so here when we increase the collector to base voltage, the depletion region width will increase more in the base region, less in the collector region. Why? Because base is very lightly doped, so that's why the depletion region width is very high here. So this is the effective width, and this width we are taking it as W. Here the total width is equal to the W effective, the total base width is equal to the W effective plus W here. Suppose if VCB is increasing, VCB value is increasing, the effective width of the base is also increasing. If the effective width is increasing means what? The actual base width will decrease. If the actual base width is decreasing means what? The width of the base is reducing means the recombination in the base is also reducing. If the recombination process is reducing means the base current will also reduce. If the base current is very less means automatically the emitter current will be very high here. So here recombination is very less, so that's why emitter current is very high here. So that's why if we increase the VCB, emitter current will increase. So here we are having one more reason also. If the charge gradient of the emitter is increases, then also the emitter current will increase here. Charge gradient will increase. Why? Because recombination is less means the charge gradient will also increase. So that's why emitter current will increase. So that's why if you see the input characteristics, if the VCB is increased from 0 to 10 volts, the emitter current is also increased. That is nothing but we will get early. We will get the emitter current very early voltages for very early voltages. So this is nothing but the base width modulation in the case of common base configuration. And if we see the output characteristics, these output characteristics we will draw for output voltage VCB versus IC here. So to see the output characteristics, first of all, we have to take the output equation of the common base configuration, that is IC equal to alpha IE plus ICBO, where ICBO is nothing but leakage current or reverse saturation current. So this ICBO or leakage current is very less than this alpha IE current. So we can take it as IC equal to alpha I. So alpha equal to IC by I. So this is the current amplification factor in the common base configuration. That is nothing but the variation in the output current is due to the variation in the input current. Why we are saying like that means if we see this particular equation, this is independent of VCB. This equation is independent of VCB voltage. So here the output current is independent of the collector to base voltage, but it is only depending upon the input current, that is IE. If you increase the IE value, the IC value is increasing here. If you decrease the IE value, the IC value also decreasing here. Suppose if IE equal to 0 means IC is also 0 milliamps. So in that case, your transistor will operate in the cutoff region. Why? Because we don't have any output current in this region. Okay. And if you increase the emitter current, you will get the next curve. We will get corresponding increase in the collector current. Similarly, if you are increasing the emitter current, in that way the collector current is also increasing. So this particular region we are calling it as the saturation region. Both the junctions are forward biased, and this particular region we are calling it as the active region. So gradually the current is increasing here. So these are the output characteristics of the common base configuration. Here, if you observe this, common base configuration means, collector to base junction is reverse biased means the characteristics are similar to the reverse biased diode characteristics if you observe here. Here, if you still increase the VCB voltage, there is a breakdown will occur across the collector to base. So there is a sudden rise of the current here. So if you flip this particular characteristics, then you can say it as the reverse bias characteristics of the PN junction diode. But this breakdown or sudden increment of the collector current will not appear in the case of transistor. Why? Because it will operate for low power regions. So this is about the output characteristics of the common base configuration. And similarly, next type of configuration is common emitter configuration. So in this case, emitter terminal, we are taking the common between the base and collector terminals of the transistor. So again, I am taking the active region of operation. So that's why emitter base junction or input junction is forward biased. Okay. The input voltage we will get it as VBE, and the input current is IB, and the collector to emitter junction is reverse biased. So the output voltage is VCE here, and the output current is collector current. And similarly for the PNP transistor also. So the difference between the PNP and NPN configuration here it is all the polarities of the batteries as well as current directions will opposite to the NPN transistor in this case. So to draw the input and output characteristics of the common emitter configuration, we are including voltmeters, ammeters as well as potentiometers in the common emitter circuit to measure input current, input voltage, output current and output voltage. So next we'll go with the input characteristics. So in the case of common emitter configuration, the input voltage is VB and the input current is IB current. So IB current is very small, so that's why we will indicate with microamperes, and the base to emitter voltage we will measure in volts. Okay, so in this case also base to emitter junction is forward biased, so we will get the forward biased characteristics of the PN junction diode only. But in this case, if you increase the collector to emitter voltage, we are drawing these particular characteristics while maintaining the different constant values of the collector to emitter voltage. So if there is any variations in the collector to emitter voltage, the input characteristics or input current will reduce here. Why? We will see again because of the base width modulation that current is reducing here. For that again I am constrained to explain that I am constrained again NPN transistor. Here collector to base junction is reverse bias, so that's why the depletion region will be more in the base region compared to the collector region, and it is very low, so very lightly doped. The total width of the base I am taking here it as WB, and this width I am taking here it as effective width, and this width is the W. So the total base width is equal to the effective width as well as width of the collector region. That is nothing but effective width is the depletion region which is extended towards the base terminal or base region. W is nothing but the width of the depletion region which is extended towards the collector region. So here the collector to emitter voltage VCE is equal to the VCB plus VBE here. From this we can say VCE equal to VBE plus VCB we can take. So in this case, if VCB increases, VCE is also increases here. So once the VCE is increases means what will happen here? Our collector to base voltage is increasing means the base current will decrease here. The base current will decrease. Why? Because the VCB increasing means the effective width of the base region or the depletion region width of the base region is increasing, so that the base current will decrease here. So that's why in this case, if the VCB increases, the IB current will decrease. So that we can observe here. If the VCE is increases, the input current will decrease here. How the VCB is increasing? If the VCE is increasing, VCB also increasing. If the VCB increases, IB current is decreasing. So from this we can say if the VCE is increases, IB current is decreasing. That we can observe on the characteristics. And similarly, if we see the output characteristics of the common emitter configuration, for that again I am considering the output current equation of the common emitter configuration, that is beta IB plus IC EVO. So IC EVO is the leakage current in the common emitter configuration. So this value is very less compared to beta IB. So we can write IC equal to beta into I. So from this we can write IC by I. But here in this case, the collector current is not independent of the VC. It is depending upon the base current as well as collector to emitter voltage. The collector current is depending upon the base current as well as collector to emitter voltage in the case of common emitter configuration. Why? Because here in this case again VCE equal to VCB plus VB. So if VCE increases, VCB is also increases. If the VCB increases, the effective width increases. If the effective width of the base is increasing means the base current will reduce here. So once the base current is reducing means the collector current will increase here. So that's why the collector current is depending upon the base current as well as collector to emitter voltage in the case of common emitter configuration. But in the case of common base configuration, the output current, collector current is depending upon the emitter current only, not on the collector to base voltage. But here it is depending upon the collector to emitter voltage also. And if IB equal to 0, the collector current is also 0 here. And if IB increases, the collector current is also increases here, just like similar to common base configuration only. We will get all the three regions: cutoff region, saturation region, as well as active region. And if you compare the output characteristics with this common base configuration output characteristics with the common emitter configuration output characteristics, the slope will be vary here. Otherwise, it is similar to both the cases. And next type of configuration is common collector configuration. So in this case, collector terminal is acts like a common between both the terminals, that is base and emitter terminals. And we are operating in the amplification region or in the active region. So that's why base to collector region is forward biased. So we will get it as VBC voltage, and output we will take across the emitter, and the output voltage is VCE voltage, and here it is VEE supply voltage, and here it is VBB voltage. So to plot the again for the PNP transistor, I have indicated here. So in this case, to plot the input characteristics, I have to take my input voltage VCB and the input current IB, which is in microamperes. And if the input junction is forward biased, means the characteristics are similar to the forward biased characteristics of the PN junction diode. So that's why we got the curves like this. So in this case, if the collector to emitter voltage is increasing, means the base current will decrease. This one we discussed already in the common emitter configuration, how the base current is decreased due to the collector to emitter voltage. So because of that base width modulation, the base current is reducing while increasing the collector to base voltage. So that's why curves are shifting rightwards while increasing the VCB. That is nothing but IB is decreasing. And while coming to the output characteristics, in the case of output characteristics, here the current amplification factor is IE by IB here. So if you vary the base current, you will get the corresponding emitter current here while keeping the VCE as constant. We will draw the output characteristics VCE versus IE while keeping the base current constant. So if you increase the base current or if you vary the collector to emitter voltage, the corresponding variation we can observe in the case of emitter current. Okay. So in this case, if the base current is increases, the emitter current is also increasing from the amplification factor. We can say that okay, these characteristics are also reverse bias characteristics of the PN junction diode. So here the curves are shifted to here compared to the common emitter configuration. That is due to the effect of the base width modulation. So this is the saturation region here. This is the active region and this is the cutoff region. When the base current is 0, we will get the cutoff region. When the base current is applying or increasing, accordingly we will get the increment in the emitter current. Then we can say our transistor is operating in the active region. And if both the junctions are forward biased, you are getting the maximum current, means that is the saturation region of operation. So this is all about all the configurations of the transistor, that is common base, common emitter as well as common collector configuration. We have already seen all the input as well as output characteristics in all the three configurations. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.